Hello everybody, and welcome to page 6 of the workbook, continuing with this sections 12.1 to 12.3. We're going to talk on this page a little bit about some methods for analyzing functions of two variables. That's the type of function that we'll be studying most often in this course. All right, so we've got a couple of definitions to lead us off here. So we're going to start with the assumption that z equals f of xy is a function of two variables. Now you might look at that and say, why do we say a function of two variables? Because they're actually three, x, y, and z. Well, what we mean is two input variables, x and y. Okay, that's the situation that we want to study here. And here's the thing about functions of two input variables. They represent surfaces in three-dimensional space. You might remember back in example 2 on the previous page, we drew the graph of the function f of xy equals 3, and we got the surface that looked like a flat plane. Okay, and the thing is, most surfaces are difficult to draw by hand. Okay, it's not as easy as drawing equations of curves in calculus 1 and 2. And so therefore we have some methods for analyzing surfaces, 3D surfaces, to break them down into two-dimensional objects, which are easier to study. Okay, and there are two things that we can do to do that. Okay, and the first part of this definition is the idea of a cross-section. We get the cross-section of a function of two variables by basically taking one of the input variables and making it constant. Either let x or y be c. By doing this, we take our surface, we take a slice of our surface, and we wind up with a two-dimensional curve, which is going to give us information about the surface. Okay, another thing we can do is to set the output variable, the z, constant. That's also taking a slice, but it's taking a slice where z is constant. And that type of a slice of our surface is called a contour or a level surface. Okay? And what we're going to do in the example that follows this is just to do an example and explore what these look like, these cross-sections and contours. Okay, so looking at the example down here, we're going to take a function, z equals f of xy equals y squared minus x squared. That's a surface in three-dimensional space, and in fact, you see a graph of it here. It's that curved kind of saddle-shaped surface. If you're wondering where this graph came from, it was actually generated by a program called Mathematica. If you took Calculus 2 here at Sonoma State, you may have seen this program before. It's very good at drawing surfaces. It just basically substitutes in a bunch of values of x and y, plots all of those, and sort of consolidates it into a surface that we're seeing here. Okay, what this example would like us to do is to start out by finding the equations for some cross-sections of that surface. Okay, and in particular, we'll start with the cross-section z equals f of 1/2 and y. All we're doing is we're taking 1/2 and we're going to substitute it in for x. Okay, so let's do that. So 1/2 and y. And remember, our formula for f is sitting here, y squared minus x squared. So we're going to take x and replace it with 1/2. And just ask, what do we get if we do the arithmetic there? Okay, well, a half squared is a fourth. And so we get z equals y squared minus a fourth. Notice that that has just two variables in it. So we're talking about a curve in two-dimensional space. You might recognize that as being the equation of a parabola. Okay, it's using the variables z and y, but it's a parabola. And because there's a plus 1 in front of that y squared, it's an upward shaping parabola. Okay, so I'm going to just make that remark here. Okay, and if you'd like to picture where that's coming from on our picture, take a look over here at the left. Okay, so notice that we've got the surface, but there's also a plane, okay, a flat surface, and notice where that plane is. It's at x equals 1/2, 0.5. That's consistent with the value of x that we plugged in over here to do our calculation. And notice where that plane slices through our surface. I'm going to just highlight that in green here. That's the cross-section that we just calculated over to the right. So the equation of that parabola is the z equals y squared minus a fourth that we algebraically calculated above. Okay. Let's move on to the next one here. And they ask us now to calculate a cross-section where y is constant. We're going to let y be negative a half, kind of do the same thing and just see what kind of a curve that leads us to. All right, so z equals f of x and negative a half. Okay, we'll go back to our formula again, y squared minus x squared, and this time we're going to plug in negative a half for y. Okay, do the simplification here. That's going to give us 1/4 minus x squared. And then the question is, what are we looking at there? Well, notice that that's also a parabola, but this time we've got a minus sign in front of the x squared, so that's a downward shaped parabola. Okay, and this downward shaped parabola is also a slice of our surface, and we can see it if we look over here to the in the picture to the left. This time y is equal to negative a half. There's the negative a half on the y-axis. And if we take a slice this time along that value of y, notice what we get where they intersect. There's that downward shaped parabola that we just found. Okay, and its equation would be the equation that we just wrote down to the right. Z equals 1/4 minus x squared. Okay, so notice that by taking a value of x or y and making it constant, we're just generating a slice of our surface. And we can see what these slices look like visually by looking at the graph. Okay, and then finally, the last thing that they'd like us to do is to find a contour where z is equal to 0.3. So we're going to let z, the output value, be 0.3 and see what equation we get for that. Okay, that's going to take us down to the last picture here. So if z is equal to 0.3, that's like taking our formula, f of xy, and setting it equal to 0.3. But we remember, okay, the formula for f of xy was given to be y squared minus x squared. And then we could ask the question, what is that the equation of in two dimensions that we came up with? Y squared minus x squared equals 0.3. I would bet that you've probably seen a formula like this, but it's maybe been a really long time ago, maybe in an algebra or a geometry course. This is actually the equation of a hyperbola that we're looking at. Okay, we've got an x squared and a y squared and a minus sign between them. And we can see that hyperbola by going over here to the left and noticing where that flat plane, okay, that's z equals 0.3, slices through our surface, and there's actually two pieces to it, here and here. Okay, those two pieces together are the hyperbola that this equation over here to the right represents. Okay, so we've reached the end of this example, and just to kind of summarize it again, cross-sections and contours are basically just about taking slices of our surface. They're giving us information about our three-dimensional surface in 2 dimensions, one slice at a time. This is a tool that we'll use throughout the semester to analyze functions of 2 variables.